Hello everyone. Today I'm going to present the computational fluid dynamics simulation of a four-blade Savonius wind turbine. Starting from fluid mechanics, the fluid mechanics is a branch of science where we deal with the uh, fluid studies regarding the fluid in motions or in static. The fluid static is a study uh, where we study for the behavior of the fluid irrespective of the time, or the hydrostatic studies, that is the hydrostatic pressure, atmospheric pressure, buoyancy, or any other behavior of the fluid. Meanwhile, in the fluid dynamics, it's a branch of fluid mechanics that studies the fluids in motion, that involves a couple of equations, or the mass the mass conservation equation that includes the Bernoulli equation, flow analysis, open channel flow, Navier-Stokes equation. So for moving forward to the fluid dynamics, it is a subdiscipline of fluid mechanics that deals with the fluid flow, the science of fluids or liquids and gases in motion. It has several other disciplines that could be the aerodynamics or hydrodynamics. Aerodynamics involves the study of gases in motion or air in motion, or the fluid flow over any object. Meanwhile, the hydrodynamics deals with the study of liquids in motion, or inside the liquid. For example, we can study the flow velocity over any object. We can study uh, changes with pressure, density, or we can also solve the other problems regarding the heat transfer or thermal management with respect to space and time. Computational fluid dynamics, or CFD, is the analysis of a system involving the fluid flow, heat transfer, associated phenomena such as chemical reaction, that by means of the computer-based simulations. This technique is very powerful and spans a wide range of industrial and non-industrial applications. For example, here are some examples for the applications of CFD. We can visualize the performance of an aircraft. We can study the thrust produced by the jet engines. We can study the flow behavior inside the jet engines, or how much the lift and drag it produces, and how efficiently the plane is passing through the fluid or through the air. Same as we can also visualize the fluid study or the flow over an SUV car. We can study any thermal management problem, or we can solve any thermal management problem. In electronics, mainly that could be uh, with fans, or liquid-based cooling, or any other thermal management problem. We can visualize the hydrodynamic problem as well. We can uh, solve or study um, the gases that are getting emitted from any plant, or due to the burning of multiple chemicals. We can visualize a chemical reaction, and we can study the emissions coming out of it. These are some of the basic applications of CFD. Moving further to our uh, problem statement today, we are gonna perform a 2D dimension transient CFD simulation of a four-blade 7S turbine operating at the rotor velocity is 12 radian per second, and the wind speed is considered as 8 meter per second. The wind turbine operating at a tip speed ratio of zero point 0.7. The aim of our study is to capture the behavior of the unsteady aerodynamics of the turbine at this operating point, uh, predicting of the time average, or we can calculate the torque that is generated. Uh, we can evaluate how much the moment is created by the wind turbine. We can also visualize the flow behavior all over the turbine. So for moving towards the geometry consists of the four blades that is with the thickness of 2 mm and made up of aluminum alloy. So we're gonna create this geometry in the Ansys workbench. So for that we have to open the Ansys workbench first. Here we are gonna select the fluid flow module in the geometry. First of all, since it's a 2D analysis, so we are going to change the analysis type to 2D. Then we're going to do the right click to edit the geometry in Design Modular. So first the Design Modular is open. We're going to set the units to millimeter. Then we can correct the orientation. We have to click on the new sketch to create a new sketch. I'm going to click on the sketch. Here we have to click on the sketching mode. After that, we can go into the settings where we can specify a grid for our own ease. We can do the grid spacing to 1 mm. Then select the draw. At first, we are going to create a circle. And we have to give the dimension to this circle, that is 38 mm. After which we are going to select again the draw, and in draw we have to create the arc. So for that I'm using arc by 3 points. You can zoom in a little bit to make sure we have selected the correct intersection point. And once we check with the alignment with the axis, we can create it. We have to assign the dimension for the arc as well. We again go to the dimension, select diameter, then we're going to select the edge that we have just created. It's going to show another diameter. So for this diameter, since we have the blade thickness of 2 mm, so we are going to create the first arc for 173 mm, which you can see. After that, we have to create another arc. So for that, I'm taking another line that is 2 mm apart. Once it is created, now select the arc by 3 points, and we are going to make one more arc here. We can zoom in and zoom out. Check with the alignment as well. So for this arc, we are again gonna give the dimension, the diameter, and select the second arc, D3. For D3, we have to assign it 175 mm. See, there is some problem. So we can always press the Control Z to undo this. We're going to select this arc and delete it. We'll create the arc again. Now it has been created correctly. Now we have to create one more line to close this open edge. We'll again go on draw, select line, and we can put the line in here, the P you see. If you see the point P, that is the identification that you have selected the correct point of intersection. Then we can zoom out. We don't need this interior circle. We only needed that for reference. We're not going to include that in our simulation. So we're going to go and modify, and we can trim the circle. Then we're going to go in the modeling. We have the closed edge completely. That is closed from here as well. That is closed from the other end as well. Once we make sure that the both ends are closed, then we can go on concepts, surface from sketches. So we can select the sketch one and then apply. So once sketch is selected, we put the operations for add the material, and after that we can just right click and click on generate. So it will create a surface for the sketch we have just created. Since we have 4 blades, so we have just created one blade, and then we are gonna pattern it. So for that we have to go to the create body transformation, then we can click on rotate. In the rotate we have to select the preserve bodies to the yes, so it will preserve the body and it will not create a new one, but it will create a copy of it. For the bodies we are going to select the surface body that we have just created. For the axis definition we can select the components. In the component, since we only need to create it in a rotation in z-axis, so z-axis is 1 and the x and y component is 0. For the angle we can create 90. Once it is created, then we can generate to create it another body. For the other two blades we're gonna do the same thing, go on create body transformation, then in rotate. This time we are just gonna select two of the bodies. At first we have to do the preserve bodies, yes. For the bodies we are gonna select, you can hold the shift and select both of them, so they both are gonna be selected. Apply. In the axis definition, components again, z for 1, and since it is 90 we're gonna make it 180. So we can see we have created the 4 blades. Once you see the preview, then you can create, click on generate to create the 4 different bodies. Now we have to create the outer circle. For that, we have to go in a new sketch, sketch 2, sketching, select the circle. From the center of the axis, we're gonna create another circle. For this circle, we have to give the dimension, the diameter, that is, we're gonna select this edge to give the dimension to this circle, that is 385 mm. So we're gonna put the 385 mm. Now we have to go in modeling and we have to create a separate body for this circle. We go on concepts. We're going to select this surfaces from sketches. In this option, we're going to select sketch number 2, so it only select the outer sketch that we have just created. Apply. In the operations, since we need both the bodies to be separated, so we are going to put this in add frozen. So this is not going to merge the bodies that we have generated. Okay. Now we have to cut the blades from this. So for that, we have to create a boolean. We'll go on create, select boolean. In the boolean, we have to select the operation, add subtract. So the target body is the the bigger circle, the bigger domain, and the tool body will be all of the 4 blades. So we can just select the bodies for the blades all together. So we can see 4 bodies are selected as a tool bodies and 1 body selected as a target body. We have to create the boolean, so we will just right click and click on generate. So this will generate a cutout for the turbine blades. Now we have to create an outer domain. For that, let's name this body first. Turbine. For the domain, we have to select a new sketch. Click on sketch 3, then we can select sketching. We can zoom out a little bit. We have to select rectangle. And we can just create a rectangle here. Now we have to give the dimension. So first we are gonna give the horizontal direction from this center point. You can always zoom in and pan from the center point and select this line. For H8, it is currently 565 mm. We have to do it 1400, or we can do it a little less, that is 1250 mm. Now we'll select the vertical. So for the vertical edge, for the upper half, we're gonna select it for 700. Then again for the lower half, or we can altogether Let's select the lower half only, and we can put that as 700 again. Now we have to just move this line. We have to give the dimension to the rear end. Control Z. Whenever it shows a red mark, that means that there has been a problem with the dimension. Okay, so again select the horizontal. Yes. Now for H14, we can move it 3500 mm apart. Okay. Now since the domain, we need to capture the inlet velocity in a more better way. So we are gonna change the front domain and adjust it to 1400. Okay, now we have enough space. We also have to create one more circle as well. Okay, now our domain has been completed. So we are just gonna create a separate body for this domain. So in the concept, select surfaces from sketches. The base object is sketch 3, so we can click on sketch 3 and then click on apply. In operations, we have to select add frozen, so it will keep all of the bodies separately. After that, we can just create on generate. So it's gonna create the two separate bodies. One is for the turbine and one is for the domain. We can right click and rename it as domain. Okay, so now our geometry has been created. We can also once again check if the geometry has been created correctly. So for both the bodies, we have to select the type, that is fluid, for both of the bodies. Okay, now we can just exit from the design modular and our geometry has been created. Now we have to create the mesh for our geometry. So right click, we are going to click on edit. As we can see, both of our bodies has been imported from the design modular. Now we have to go on mesh. In the mesh, we first have to define the general element size. For the general element size, we can put 20 millimeters. First, we have to insert the method selection. We're gonna select two of the bodies, so first body and the second body as well. Click on apply. Since we need the triangular mesh, so we have to select the method as triangles. Now we have to insert the sizing. So for the outer domain, we can select the body, click on apply, and we will select the element size to be 16 mm. We'll give the behavior as hard and turn off the capture curvature option. So it will only create the mesh as you have instructed. We now have to give the sizing. So for that, we have to first hide the body for the turbine. Right click, insert, we'll create sizing. This time we have to select the sizing for the edge. So we're gonna select the edge selection. Apply one edge. For this, we are keeping the element size for 4 mm. Capture curvature to be off. Behavior to be hard. Now we are gonna show the turbine body and hide the domain body. First, we have to again select the outer edge. Apply. We have to match the element size for the bodies. So for this one, I'm going to put 4 mm again. It is better to visualize that the interface of both the bodies matches with the same element size, so it will create more elegant meshing without any sort of pinching. Now we can insert sizing for the blades as well. For the blades, you can just hold on the control and use the left click of the mouse and just hold it all together. So it's going to select all of the edges. To make sure, you can zoom in and check. Once it shows the green line, that means that edge has been selected. Here we see that one edge is not selected, so we have to press the control key again and then we select. Okay, now all of the four edges for our blade have been selected. You can also verify it from the quantity here that we have selected two edges for the blades. That includes all four edges. For this, we are going to give the element size for 2 mm. Capture curvature is off, and we can put the behavior as hard. Now we have to again select the sizing, but for this time we have left some of the edges in for the blades. Since these edges are very small, so we are giving a separate sizing for these edges. we have to select the other end as well. Since there is two ends for every blade, so again we have to verify that the final quantity is 8 edges. If the quantity is not 8 edges, then that means we have left one of our end. Okay, so we have selected all of the edges. Once you click on this sizing, it's gonna show the 4 edges, as you can see. For this one, since they're very small and the thickness is 2 mm, so we're gonna divide that into 4 parts so we can put the size for 0.5 mm, or we can divide that for more elegant mesh, we can divide that into 8 parts so we can put 0.25 mm. For better transition in for the mesh around the blades, we're gonna add the inflation geometry. For the geometry, we have to select the turbine geometry, and for the boundary, we have to select the 4 edges of the blade. We can also check that all of the edges has been selected or not. Like this edge is missing. So we are gonna give the maximum layers of 5, and the rest remains same. Now we can right click to show all of the bodies. Now we just create the mesh and right click to generate the mesh. As we can see, our mesh has been created. So we have to zoom in a little bit and we can check for the inflation and the mesh on the shortest edge. Since there is a lot of pinching, so we are gonna reduce this mesh size. It is 4. You can put it on 0.5. Click generate again. Now we can check the edge. Edge sizing is more better and less pinching. For more refined mesh, we can modify the mesh size. for the blades from 2 mm to 1 mm to make it more refined. Depending over the geometry, since we do not require a lot of precision in the domain zone, but we need refined mesh around the blade so it will capture the behavior of the velocity and the fluid around it in a more better and perfect way. We can always zoom in and check. Still there is a little bit of pinching, so I'm gonna insert one more sizing that is for the face of the turbine geometry. Select the face and we're gonna assign it to 4 mm so it will better align with the other element size as well. Again, we put on generate mesh. So depending over the geometry, you can always assign more sizing to the areas where you need more precision and where you need the better, where you need to capture the behavior of the fluid in a more better way. Okay, so now the face meshing causes the turbine face to be at one singular style or one singular element size. So we can see that the boundary has the cell alignment with the interior face of the turbine. Since our mesh has been created, now we have to select the edge to give the name selection that will help us in the next step. So we are just gonna go on click, select the edge, right, select the edge and right click, create name selection. So we will name it as inlet, and for the edge at the right hand side of the domain, we'll right click and create the name selection as outlet. We'll hide the turbine geometry, select the edge, and we will create another name selection that is interface out. This is actually the connecting interface for the turbine geometry and the domain geometry. Now we'll hide the domain geometry. For the turbine, at first we will select the outer edge and create the name selection again, that is interface in. Now finally for the last, we have to select the edges for the blades to create a name selection for the blades. So we'll go to the mode and select the box select. And here you can just drag the box to select all of the edges. To make sure, we can create another name selection, and here you can see the 4 edges being applied, but we have to get all of them, so we are just gonna select them. Here the quantity of our edges should be 16. Now we have to select the left ends of the blades. Every time when you are penning and you have to select, you have to remember to keep pressing the control key when you are selecting the edge, so the other edges will not be unselected. So we have to check one more time. All of our edges has been selected. So we can keep pressing the control key and then apply. We can see that all of the 16 edges has been selected. We're gonna rename it for blades. Now the name selection has been completed. And the mesh is also being generated, so we can move towards the setup. So we're gonna save the project first. Once it is saved, we can close this window, select the right click on mesh and click on update. Once the mesh cell has been updated, then we'll right click on the setup, select the edit. Here we're gonna select double precision and the solver processor to be forced. That depends upon the capacity or compatibility capability of your device. So you have to wait a little bit until the setup has been read by the Fluent. Once the complete geometry is being imported to the Fluent, you can see in the console box that all of the zones has been written and imported. This shows that your geometry has been completed imported without any sort of errors. Since it is a transient simulation, so for the time we're gonna select transient. From multiple models of fluid dynamics, we're gonna select the viscous equation to be K epsilon, second equation. You're gonna press OK. After that, we have to make sure the material is air. We're not gonna make any changes for the density and viscosity here. So just click on change and create and close. Now for the fluid, we have to go on turbine as we select that name in the geometry setup. So always renaming in the while making the geometry will help us in the while the setup. So for the turbine, we have to click mesh motion. Here the rotational velocity is 17 radians per second. We're just gonna click apply and close. Now we are gonna select the boundary condition. So for the inlet, just double click on inlet. You have to select magnitude and direction. The velocity magnitude is 8 meter per second. For specification method of the turbulence, we're going to select the intensity and the length of the scale. And click apply, close. Then for the outlet, we have to make sure that the same configuration has been selected. Since the gauge pressure is 0, so we do not have to change anything here. It's just going to change the turbulence setting and apply. Now for the blades, we have to select the boundary condition for the blades. So we have to assign that on moving ball, and we'll assign that on rotation to make sure it captures the rotational behavior of the blades. Then we click on apply and close. Now in the method, we will select the turbulent kinetic energy to be second order and dissipation rate for the second order as well. Now in the monitors, we have to select the residuals and we will assign the continuity to be 1 exponent minus 5. So for this continuity, this shows the precision for your simulation and the solution you are getting. Now, since we have to capture the force and moment of the turbine, so we're gonna go in report definitions We have to select a new. In force report, we can select force. For the X component, we can select the report file and report plot option to make sure when it captures the reading, so that will be written in the report file and the plot will also create it. For the zones, we'll create the blades as we need that for the blade. Okay. Now we have to do the same thing for the Y component. Force Y, we'll put the X 0 and Y as 1. Select the blades and we can press OK. Now we have to capture the moment as well. Since the moment will be in Z direction, so we have to make sure that X and Y values are 0 and Z is 1. Report output type is moment and it is for the blades. We have to click OK and close. We can also check that as well, that report files includes force X, Y and moment Z. For the plots, we need the force X plot, force Y plot and moment Z plot. Now we'll go in initialization and we'll proceed with the hybrid initialization. For every problem, when you uh, proceed to the step of initialization, you can also check in the console box that that your solution or your boundary condition has been read correctly and your continuity uh, will can go to 1 exponent minus 9. That shows that you have selected all of the correct boundary condition and there is no problem with the model that you have created. In the results, we need the contours for the velocity and pressure uh, plots. So we'll double click on contours. We'll just click save and display and close. We'll do the same thing again for the pressure. And we'll keep it selected on the pressure and static pressure. Click on save and display, close. So now we need the animation. So we'll go back in the calculation activities. Here we can see the option for solution animations. We can double click the solution animation. So for our first animation will be for velocity. For velocity animation, we need the velocity controls to be selected and OK. We have to do the same thing again, this time for pressure animation. And we will select the pressure controls and we select OK. Once everything has been selected, we'll go on run calculation. Here we're gonna decide the number of steps to be written. That is 400 in my case. For the time steps, that means the interval that we need for to capture our animation correctly. So for this problem, I'm going to give it to 0.002. For the maximum iterations, we will select initially for 30, and the rest of the information will remain same. For the time step, we have very less, so we will do it 0.02. We can always go to the top one and we can check our boundary conditions again to make sure nothing has been left. So here for the viscous, we have defined the k epsilon omega 2 equation. So we can just select OK again. For the material, fluid is air. For the cell zone condition, we can check the turbine again, that is with the mesh motion, and the rotation velocity is given. For the boundary condition, we'll check again that the inlet has been selected with 8 meter per second of the velocity inlet. For the walls of the blade, the right configuration and the right setting has been selected. In the report definition, we can see that we have selected the force in the x, force in the y, and moment in the z direction. The residuals has been selected for 1 exponent minus 5. Now to make sure, we will do the initialization again. And we can proceed with the calculations. Okay, so now our calculation has been started. So we have to give it a little bit of time. We can also see that it is going to read all of the windows for the output we require. That includes the contours of the velocity magnitude, the static pressure, the moment, force in y, the force in x, and static pressure. For the continuity, we can check with the scaled residuals. So we have to give it a little bit of time to get our simulation completed. Okay, so now we can see that the simulation has been completed, and we have all of the plots for the continuity and the contours for the static pressure and velocity as well. We have the force x plot that has been generated during the simulation. We have the force for the y velocity. We have the moment generated, and we have the scaled residual as well. We can also check for the contours of velocity. So we have here we have the velocity controls as well. Now we have to write the animation. So for the animation, we have to select the playback. In the playback, we have to unselect the use stored view to better write the simulation when it is zoomed in. So we can select the particular view so that while capturing the animation, it won't be zoomed out. It will be perfect according to the visibility. We can slow down the replay speed as well. We can put it on play once, that will capture the animation once, or we can also select the auto repeat option. With that, we have to select the right record format in the video file. We have to select the velocity animation because that is the velocity animation. We have to select that and zoom in again. We can also adjust the legend. And we have to click at the right once we proceed with the right, since I have already written the animation. So click on write and it will write the complete animation, and after that we have to do the same process again, and this time we will do for the pressure animation that we have created. Select the video file and write. Once the animation has been written, we have to go to the same files where we have stored our workbench file. So in the same folder where we see the Savonius Turbine files, we have to go to DPO0. We have to go to triple F. After that, we'll go to the Fluent. And from the Fluent, we can see that both of our files has been written. One is for velocity and the other one is for pressure. So we are now gonna visualize our animation that we have created from the simulation. Put that on loop. Now we can see and visualize that we have created the correct flow simulation for the 4-blade Savonius turbine. This is the velocity animation where we can also see how the velocity is changing and uh, how the blade is rotated. Once in the start, we see a little bit of turbulence in the flow, and after that, the flow got stagnant according to the velocity of the wind turbine and the velocity of the air as well. So we're gonna close this one and check for our pressure animation. To slower it down to the uh, to more time steps, we can reduce the step interval that we have selected earlier point for 0.5 0.25 or zero point 0.2, I guess. So we can reduce the time step more. So our simulation will be treated in or more slow motion. So here we have gone through the geometry creation, the meshing, and after meshing, we have gone through the complete simulation setup and how to visualize the animation for any sort of problem or any sort of safety problem. So we're going to close this one as well. Once everything is done, you have to save the project. Okay, so now this was the complete representation where we got the uh, velocity contours, we got the pressure animation, we have evaluated the force along the x component, force along the y component, and the moment generated by the wind turbine during the simulation. After that, we can further evaluate the power or the torque produced by the wind turbine as well for our further calculation. That depends on what we need to evaluate. All right, thank you so much.